Hello everyone, I'm Vikram Madduri here. Welcome to Softech. In this session, we're going to discuss about machine learning, chapter 1, part 7 of it. And we'll be focusing on mostly the naive-based rule here in this particular session. So we have 6 easy steps to learn naive-based algorithm, which is the most important, if at all, if you're looking out for learning Python and R or any of the machine learning concepts. Now, what is naive-based algorithm? Naive-Bayes algorithm is basically based on Bayes' theorem with an assumption of independence among predictors. In simple terms, a naive-Bayes classifier assumes that the presence of a particular feature in a class is unrelated to the presence of any other feature. For example, a fruit may be considered to be an apple if it is red, round, and about 3 inches in diameter. Now, even if these features depend on each other or upon the existence of other features, all of these properties independently contribute to the probability that this fruit is an apple, and that is why it is known as naive. Now, we also in the previous sessions, if you remember, we also have taken another example in which we have taken the HIV test case in which we have two different predictions which are independent of each other. So they're not dependent on each other. So naive-Bayes model is easy to build and particularly useful for very large data sets. Along with simplicity, naive-Bayes is known to outperform even highly sophisticated classification methods. So this theorem provides a way of calculating posterior probability, so P of C by X from P of C and P of X and P of X by C. Look at the equation below. So let's see this equation. So P of C of X is that this is a posterior probability would be equal to the likelihood into the class probability, prior probability, and the predictor prior probability. So let's see P of X by C into P of C by P of X is the posterior probability calculation that we do. So now here P of C by X is equals to P of X1 by C into P of X2 by C into P of X3 by C. So we have laid a lot of likelihood probabilities that we are going to calculate and then come back and conclude the posterior probability. Now here P of C by X is the posterior probability of class C target given predictor X attributes. P of C is the prior probability of class. So P of X by C is the likelihood, which is the probability of predictor given in a class, and P of X is the prior probability of the predictor. So this is very important. We need to understand this formula, and if possible, you have to remember this always. And this is very important for the posterior probability. Now, how naive-Bayes algorithm works? So let's understand it using a simple example here. I have a training data set. Let's take the example of a training data set of weather and corresponding target variables. The play. Suggesting possibilities of playing. Now we need to classify whether players will play or not based on weather condition. Let's follow the below steps to perform it. Let's convert the data set into frequency table and create likelihood table by finding the probabilities like overcast probability, that will be 0.29, and probability of playing is 0.64. Now let's say the weather is like sunny, the play is no, and if it's overcast is yes, we have rainy, yes, and what is the probability we are forecasting, what is the probability of the match happening, and overcast probability and the probability of playing. So the probability of playing is what we have to calculate. So then we have the weather and play. So if it's too sunny, it says no, and if it's overcast, yes, and if it's raining, no, and if it's raining again, no. So these are the various probabilities that we have for weather and play. Frequency table is like, here we have the frequency table where weather if at all, if the weather is overcast, then yes are 4, rainy 3 no, and 2 yes. Now, if it's sunny, 2 no's and 3 yes. The grand total would be how many total number of no's are 3 2, the grand total is 5, and how many number of yes is 9. So the grand total of no's is 5, the grand total of yes is 9. So the likelihood would be calculated in overcast would be 4, rainy 3, no's, and yes 2, and sunny 2, and sunny for sunny 2 no's and 3 yes. All together, put together, we have 5 no's and 9 yes. So if we calculate the probability 5 by 14, the total number of probabilities that we have is 14, and 5 by 14 is what we have for no's, and the possibility of yes is 9 by 14. So that would be 0.36 and 0.64. This is how we actually calculate the likelihood. And once we have calculated the likelihood, we have overcast. What exactly is the weather overcast probability is 0.29, and for rainy, yes is 5 by 14, no is overcast we have 4 by 14, and that's 0.29. That's yes, we are calculating yes. And the overall probabilities that we have is like complete probabilities would be 3 and 2, and that will be 5 by 14, that's 0.36, and we have 2 and 3, that's 5 by 14 is 0.36. So this is how we are actually calculating the overall output. But here the complete final yes would be 0.64 and no would be 0.36. When we calculate this Naive-Bayes equation to calculate the posterior probabilities for each class, the class with the highest posterior probability is the outcome of prediction. So the problem here is like the players will play if the weather is sunny. Is this statement correct? So we can solve it using above discussed method of posterior probability. So like say if you have probability of yes by sunny is equals to probability of sunny by yes into probability of yes by probability of sunny. When we calculate this, here we have probability of sunny by yes is equals to 3 by 9, that's 0.33. Probability of sunny is equals to 5 by 4, that's 0.36. And probability of yes is 9 by 14, that is 0.64. So the total probability of yes by sunny is equals to 0.33 into 0.64 by 0.36 is equals to 0.60, which has a higher probability. So the Naive-Bayes uses a similar method to predict the probability of different classes based on various attributes. This algorithm is mostly used in text classification and with problems having multiple classes. What are the pros and cons of Naive-Bayes theory? We have it is easy and fast to predict class of test data set. It also performs well in multi-class predictions. When assumption of independence holds, a Naive-Bayes classifier performs best compared to any other models like logistics regression, and you need less to less training data as well. So it performs well in case of categorical input variables compared to numerical variables. So for numerical variables, normal distribution is assumed. So the bell curve is a strong assumption. And the cons would be if categorical variable has a category in test data set which was not observed in training data set, then model will assign a 0. The probability and will be unable to make a prediction. This is often known as a zero frequency. To solve this, we can use the smoothing technique. One of the simplest smoothing techniques is called Laplace estimation. So on the other side, Naive-Bayes is also known as a bad estimator. So probability outputs from predict probability are not to be taken into seriously. So another limitation of Naive-Bayes is the assumption of independent predictors. In real life, it is almost impossible that we get a set of predictors which are completely independent. So applications of Naive-Bayes algorithm would be real-time prediction. Naive-Bayes is an eager learning classifier, and it is sure fast. Thus, it could be used for making predictions in real time. So then we have the multi-class predictions. This algorithm is also well known for multi-class prediction features. Here we can predict the probability of multiple classes of target variables. And then we have the text classification, spam filtering, sentiment analysis. Naive-Bayes classifier is mostly used in text classification due to a better result in multi-class problems, and independence rule have higher success rate as compared to other algorithms. As a result, it is widely used in spam filtering, identifying spam emails, and sentiment analysis in social media analysis to identify positive and negative customer sentiments. The recommendation system would be naive-Bayes classifier and collaborative filtering together builds a recommendation system that uses machine learning and data mining techniques to filter unseen information and predict whether a user would like a given resource or not. So now how do we build a basic model using naive-Bayes in Python? So again, learning Python would be based on the independent library that we have in Python, which I'm going to soon start as soon as possible. But will help here to build a naive-Bayes model in Python. So I'm just going to explain you a basic uh, code which can predict with which we can represent the naive-Bayes in Python. There are three types of naive-Bayes model used in the line library. So we have Gaussian. It is used in classification and it assumes that features follow a normal distribution. Then we have multinomial. It is used for discrete counts. For example, let's say we have a text classification problem. We can consider Bernoulli's trails, which is one step further, and instead of word occurring in the document, we have count how often word occurs in the document. You can think of it as a number of times outcome, number of a number is observed over the n trials. Now in the Bernoulli, the binomial model is useful if our features vectors are binary. It might be zeros and ones. Uh, One application would be text classification with bag of words model, where the ones and zeros are word occurs in the document and word does not occur in the document. So that if it's a word occurs in a document, it's one, and word does not occur in the document is zero, respective. So based on your data set, you can choose any of above discussed models. That is the three models: the Gaussian model, and multinomial model, and Bernoulli's model. So below is an example of Gaussian model. So this is something which we have for Gaussian model, in which we have a Python code that we have here. This is the Python code that you can just uh, take a screenshot of it, and then you can start working on it in the Python. Now this is the Gaussian classifier. This is the Gaussian classifier that we have here. Output is what we have. Now the R code, the same thing, we can do it in the R code as well. So this is the R code that we have. Above we look at the basic name-based model. You can improve the power of this basic model by tuning parameters and handle assumption intelligently. Let's look at the methods to improve the performance of name-based model. I'd recommend you to go through this document for more details on the text classification using name-based. So to improve the power of naive-Bayes model, here are the some tips. So if continuous features do not have a normal distribution, we should use transformation or different methods to convert it into normal distribution. If test data set has a zero frequency issue, apply smoothing techniques, Laplace correction to predict the class of test data set. Remove correlated features, as the highly correlated features are voted twice in the model and it can lead to overinflating importance. Then we have naive-Bayes classifier has limited options of parameters tuning, like alpha is equals to 1 for smoothing and fit is equals to prior. And to learn class prior probabilities or not, and some other options like we'll look into that details. I would recommend to focus on your processing of data and the feature selection. You might think to apply some classifier or combination techniques like ensembling, bagging, boosting, but these methods would not help. Actually, ensembling, boosting, bagging won't help, since these applications is to reduce variance. Neighbors has no variance to minimize. Okay, thanks for watching this session. So share it with your friends. It might help them as well. So you can contact us if you're training at info@jhsoftware.com. Have a great day.